What's up, YouTubers? Today I got a fun video, a treat for you guys. I got an email from a guy that said, well, since there's no warranty really on this thing, why don't you tear it open and at least see what it looks like inside? And I agree with him. I was planning on doing it anyways, but it just so happened I got some downtime tonight. So I figured, why not take the case off and look at it. Now, I'm not an electronics expert. I won't pretend to be one. I won't tell you I'm one. As a matter of fact, I told you I'm not. So I may incorrectly label components of this. We'll have to see when we get into it. I do know the principle of how these work. It's pretty simple. But yeah, I guess let's start tearing into it and see what we got. Nah, I think that's the wrong tool to be using. All right, let's get this sucker opened. Now, I have not actually opened this ever. I have no idea what we will find in here. I think I gotta take this. Yeah, it does have a factory seal here, just so. Avoid opened warning. That's pretty humorous. Around here, we'll just ignore that. Goes without saying that you shouldn't be doing this if you have no idea what you're doing, and not only that, you probably shouldn't do it while it's plugged into the wall. Oh, look at that. That's cute. Well, ta-da! Very simplistic. I don't know how much we're going to be able to see and learn about in here, but let me zoom this in for you guys. All right. Let me take a look over this. You can look over it with me. Huh, okay. Couple things to note here. So, most of the components on here have heat sinks. One of the good things is this little computer case fan is blowing directly on the heat sink, so that's a plus. Probably keep them from melting. But we're not going to be able to see really a lot of what different components do simply because they're obscured. And I'm sure I could like pull these heat sinks off and whatnot, but honestly, the way that this is constructed, I don't know that I'm going to be able to get them off safely and actually put them back on. The two main outputs are just bolted through the board. Interesting. So this here is the main transformer. It's always been interesting to me that when people talk about like, oh man, you know, I miss old transformer welders and they're all, you know, they're better, or people like newer welders, inverters they call them, and they don't realize that pretty much every welder has a transformer in it. Now this is an inverter design, and however, it still uses a transformer because you have to take your wall outlet power, which is either 120 or 240 volts plus or minus, and you have to convert that to lower output DC or AC power, because your wall outlet is, say it's 240 volts on a, you know, a plug for like a welder. Well, you're not outputting 240 volts when you're welding, you're outputting like 20 to 30 volts at much higher amperage. So you need a transformer to help you with that. And that's what this guy is. The difference is these modern inverters run the transformer at a lot higher frequency than the older units, which is why they're so much more efficient, and you can use a transformer of this size, which, I mean, it's not really that big, and you can get 140 amps of output out of this whole machine without needing a transformer that's like the size of, like, I don't know, a couple grapefruits. So it's just a change in the design of how the transformer works. And you know what, speaking of that, because there's really not a whole lot I can talk about here because everything's obscured and I can't really test a whole lot. I guess to make a video out of this, why don't I explain some things that at least will be interesting. All right, so we can't really see many of the components in here, and I don't really feel like taking it all apart down to bare components, and it'll probably never work again, and I kind of want to use it for future videos maybe, and for the portability of it. So I thought, why not just do a little explanation very simply of how this little welder works, and it goes with most welders. I mean, stuff like this, especially stick welders, are very simple devices. So let's start out by drawing, this pen works, there we go. This is our power line coming in. This is our little welder box. And then this is our put positive, negative output, and I'll depict this as well. So our power coming in to the welder is, in this case, we have it wired for, we'll say, 220 volts. So in North America, it could be 220, could be 230, 240, 250, depending on where you are. I've measured my wall outlet. It's somewhere around 230 actually volts AC. And this is on a 50 amp circuit, but that doesn't matter. I mean, you can plug this in a 30 amp circuit as well. Now in North America, we're 230 volts in my case, and we're at 60 hertz. The rest of the world oftentimes uses 50 hertz. The hertz is how often, and I'll draw a little depiction here for you guys. Okay. This is the AC waveform, and this is how it comes from your power plant. And the power coming out of your wall, goes from both positive to negative. So anytime on this graph, when it goes up here, there you go. When it goes up here, it's in the positive. When it goes to here, it's negative, okay? Now with 230 volts, the spread between, because to get that voltage, you need two wires. The voltage spread between the two is 230 volts here. So when you're measuring from this point to this point, the difference is 230 volts. This device can also run on 115, 110, the lower voltage, but we're using it on 230, what I have. So the problem is that what the power company delivers us, which is AC 230 volts, 60 hertz, is unusable for stick welding. The reason is stick welding operates approximately, we'll call it 18 volt to about 30 volts, depends on rod size, arc gap, all of that. So 18 volts to 30 volts. That's way lower than 230 volts. If you were to try and weld with 230 volts, well, first off, you'd probably get electrocuted because the arc would jump to your hand through the stinger. So that's no good. And second off, your arc gap, I mean, it would maintain an arc super long. It's dangerous and it's not functional, especially because, like I said, this is at most on a 50 amp circuit, okay? So what we need to do is we need to take that 230 volts 50 amp and we need to bring it down to 18 to 30 volts, and this machine welds between 10 amps and 140. So how you do that is you lower the voltage by using a transformer. And what a transformer does is it, and I'll draw a depiction of one here. All right, depicted here is a simple transformer, and I'll put up a picture of what one looks like. The transformer in this welder operates similarly, it's just a little different of design. But the whole theory of a transformer is that you have essentially an input coil and an output coil. These coils have differing numbers, wraps of wire around the actual laminated steel core. And these wires are insulated. So like if you can see in here, you see how this wire, like it's not bare wire touching this transformer core, okay? It's got plastic sheathing on it. So it is insulated. So you have insulated wire around a steel or ferrite or some kind of material core. Well, when you have two coils of wire, or let's just focus, when you have one coil of wire and you pass electricity through it, if you remember, if you take a nail and you wrap it with electrical wire and then run a 9-volt battery through it, all of a sudden that nail picks up other pieces of steel because it's an electromagnet. Well, the same theory applies here. So you wrap a coil of wire around a core and it's isolated from that core. That wrapping creates an electromagnet. Now, if you didn't have a core and you just had two spools of wire next to each other, like let me grab a couple sockets. This will make a little bit more sense. So if you just had two cores of wire, say this is all wrapped with wire and they're close to one another, and then you impart an alternating voltage on this side, this electromagnetic flux that's created will come over and impart a change in voltage on this side, which is this side of the transformer. That's the output side. The purpose of having this laminated core here, which, like I said, the wires are not shorted to, they should be isolated from, is that it allows that magnetic field change, a change in the flux, to be essentially isolated and not leak out to the surrounding environment. Like if you just had two wrapped coils here, you're going to get a lot of leakage of the magnetic field, the flux around everything. By putting a core around it, you're keeping that field within, mostly within that transformer. Now, in the case of this welder, it uses a toroidal ring, as it's called, which is more efficient than the older school transformers that you're going to see, which depict more like this. So anyways, the whole goal of the transformer is to take our input voltage, which in the case of this unit is 230 volts AC, and then lower the output voltage. So the ratio of how many turns or windings of wire on the primary side versus the secondary side gives you the step up or step down in voltage. So if you had, say, 10 wraps on the primary side and 5 on the output, you would, that's a 1 to 2 step down. So you would lower your voltage from 10 to 5, it would be, so at 220 volts, you would step down to 110 on the output. Now the amperage that you can pull out of it would actually go up, okay? The reason being is that as you half the voltage, your amperage is double. So a simple 10 input, 5 output would give you, so we'll call it 220. Let's just volt in. That would give you 110 volt out, and instead of 50 amp, or well, in this case, it's we'll just say 50, even though it's nowhere near that 50 in or 50 amp. Let's draw amp in. It'll give you 100 amp out. Now, if we change that again and say only had like 2 turns versus 10, that would increase our amperage again and lower our voltage. So the whole theory is that with a welder, like we need to get down to 18 to 30 volts. So a range, maybe a peak of 35 volts max. And remember, the voltage is, the arc gap of your rod controls the voltage, but the most voltage we would need is say 35 volts, and then we need 140 amps output. So getting that out of this is simply a matter of getting the ratio correct on the transformer for the winding on the primary and the secondary in order to get the correct max voltage, and then the amperage is just an effect of how much your circuit can pull out of the wall. Hopefully that makes sense. I know I'm really kind of oversimplifying some things and covering stuff a little bit too quick, but all welders have transformers. The difference with this versus like an old school unit that's like 100 times its size is that this takes, and rather than just taking your wall outlet power and converting it to output, this is more typical of like a Lincoln Tombstone welder, okay? This unit converts the power before it gets to the transformer to DC. And let me just draw this real quick for you. And I'll draw how it is here. So this is a simple circuit diagram, and I'll go through what's going on in each step. And I'm not an electrics expert, so if you feel like I'm saying something wrong, I have no problem with you leaving comments and stuff on this. I'm just simplifying how one way this unit could actually be working and give an explanation. So we have AC power coming out of the wall, alternating both positive and negative, okay? This unit will then take that AC power and it will either do one of two things, because our output is DC on this. It's gonna take that AC and convert it to DC power, just straight power, and it does so through what's called a bridge rectifier. And all a bridge rectifier, and this is, I'll just put a B on it. All a bridge rectifier does is it essentially, I'll draw it up here. As your waveform goes both positive and negative, it takes and changes to where when the power goes negative, and it creates it on the positive side, and it creates essentially a rippled pattern of DC because it no longer is alternating positive and negative. So it flips very simply with a series of gates to where the power is now all on the positive side with nothing on the negative. So you would eliminate that. All the power is on the positive. The problem with this is that you're still hitting a point of zero voltage between the high peak, which is a problem. So oftentimes the input after the bridge rectifier or whatever have you that they're using, they might use capacitors, which is probably what these are used for. Again, I'm not positive on this. I don't have a schematic. And what that will do is it will change that ripple pattern to more or less something closer to DC output. That's smoother. Can be used to smooth the DC. That could be what this is using. Now, it sounds ridiculous, but they take AC power, convert it to DC, filter it, and I'll draw two capacitors here because that may be what these are used for. They filter that, and then they input it to what's known as a IGBT. Basically, we'll draw that as that. IGBT. I believe that's internal gate bipolar transistor. I'd have to look it up, it's been a while. Nope, I was wrong. Insulated gate bipolar transistor. It's basically a series of gates and they're insulated from one another so it doesn't short out. and it works very much the same as like a one-way diode that you'll see in a full bridge rectifier. It's just controlled by a computer, if that makes sense. It's been a while. The whole purpose of an IGBT is to create an output of whatever you want. So you could have an output that's created that's a sine wave. The difference is that because it opens and shuts gates which allow voltage to either be positive or on the negative side. The IGBT, an older school like a Lincoln Tombstone welder doesn't have these. Newer inverter welders have these. What this gives you complete control over is the waveform of AC. Now, if you remember, out of your wall is 60 hertz. Okay, using an IGBT controller, you could actually change that 60 hertz where 60 times a second it's alternating positive and negative. You could convert it to 240 hertz. Okay, you could change it to 1,000 hertz. The reason you would want to do that is your transformer, which in this case uses a toroidal transformer, the higher the frequency, the more efficient it is at transmitting power. And what I mean by that, maybe that's not the correct term, but when you open up big like Lincoln Tombstones and old stick welders, they don't have any of this in front of the transformer, and a transformer has to operate off of 60 hertz, and that is why the transformers in those things for like a 180 amp welder is like the size of a shoebox. And the reason is that operating at 60 hertz out of the wall is extremely inefficient, and you cannot get the output out of that without a very large transformer. So by creating an IGBT module and putting it ahead of your transformer, it allows you to get high enough frequency to get super high efficiency, which allows you to downsize your components. So that is why, like, this little guy is able with this small of a transformer to actually output 140 amps versus the transformer in a 140 amp old school welder would be bigger than this whole unit. And that's simply because they run off of wall frequency, they don't manipulate it. In case you're wondering to yourself, well, if higher frequency than 60 hertz is more efficient for a transformer, why on earth do we transmit 60 hertz and not say 1,000 hertz? And the answer is that on a small scale, it works more efficiently. However, we have an issue of power distribution where long wires have to carry a lot of voltage and current, and higher frequency causes issues dealing with the resistance of the wire and how it uses the wire to transmit power. So in a simple terms, in distribution, it's less efficient, and that's why we chose to use 60 hertz. Now, to go back here, like I said, you're starting at 240 volt, 60 hertz. You're converting it to DC, then you're converting it back to AC. And the reason is that transformers do not work on DC. They need a change in the magnetic field, like on this description, to impart an electromotive force, I believe it's called, on the other side of the transformer. So without alternating, there is no change in flux, there is no change in magnetic field, therefore there is no change in the output. So you can't have this transformer function on DC, which is why you need this. Now, this machine may somehow, rather than take a bridge rectifier, it may directly just take the frequency and manipulate it with an IGBT module to change it from 60 to 240 hertz without rectifying it to DC first. So essentially they just take straight AC from the wall and then use an IGBT module to change that. I'm not sure on that. I would imagine they're turning it to DC first simply because it's so simple. When you have a straight DC current like this at say 200, we'll call it 240 volts, right? Straight DC, you can take and open and create a waveform using that by opening and shutting those transistor gates to create whatever waveform you want. You could have it look like that. You could have it look like this. You could have it even more, if I can even draw small enough, like that. You can manipulate the frequency. So this is my guess as to how the transformer end of this that feeds it, you have higher efficiency. And then the transformer, because this machine welds on DC output, you then have to use a bridge rectifier of some sort to change it back to DC output. Now, if this was an AC welding machine, you wouldn't need to bridge rectify it on a DC output at all. You just wouldn't need to. You would just keep it at AC output, what it would be on the secondary winding of your transformer, if that makes sense. But this is doing the same thing as it does up here. It's just taking that AC waveform, which looks like this, and then it's just flipping the negative to the positive, okay? And now your waveform turns into that, and then it will use either a capacitor or a choke, as it's called, to just try and smooth it out a little bit more, like that. So your constant current DC output is smoother. Now, if I had an oscilloscope, I could hook it up to this welder and we could actually look at the output of it and see how clean of a signal. Like my Miller Dynasty, I'm sure that output of DC probably looks exactly flat, would be my guess. I have a feeling that this guy's output is more like this, where you still have some ups and downs. It's fairly smooth, but it's not perfect DC output. And that's simply because the components necessary to create a perfectly flat DC output from an AC source are expensive, and this is the opposite of an expensive unit. But with all of that in mind, again, you know what, I'll take that away, not to confuse you guys too much. So like I said, I'll just draw, again, a very simple depiction of this. Like I said, all it does is it takes 240 volts, we'll call it, 50 amp circuit, goes in, takes that alternating current, so we'll depict it here. Alternating current, converts it to DC current, so it no longer alternates. Then it uses a IGBT module to take that DC straight current and change the output to probably, instead of 60 hertz, it converts it, I'll just take a guess and say 240 hertz. So it converts it to 240 hertz. The amperage and everything is still the same, and then that gets fed into a toroidal transformer, which the primary side is going to be 240 hertz, say 50 amp. So I'll draw that down here. And it's not 50 amps, it's going to be less than that because this unit doesn't pull that, but we're just simplifying it. 50 amp, and it's converting that from the primary to the secondary to, say, 240, and it'd be 240 volts. And it's converting that to 35 volt, 140 amp output, and that is then rectified to DC. And that stands for bridge rectifier. Now, realistically, the bridge rectifier would actually be over here. But to give you an idea, so very simple. Take AC, convert it to DC, use a switch, a series of switches to convert the frequency of the switch to positive to negative to feed to a transformer so it's efficient. And then the transformer converts high voltage, low amperage to low voltage, high amperage AC output, and then that AC output is converted back to DC output, which is what this machine welds on. One of the things I didn't mention is that in the case of this machine right here that we have here, is how it can actually control the amperage is this IGBT modules are actually controlled by like an onboard computer. It's possible that they're controlling the amperage output by controlling the AC waves. So by increasing the voltage or the open and closing of these gates on here, they can impart a control on the overall voltage over time on the primary side of the transformer. And by manipulating the primary side voltage versus the second, it will change the secondary output. And like if we look here, like going back to here, if rather than putting 220 volts in, we put 110 volts in, that will half our output. So in this theoretical transformer, if we're putting 220 in and getting 120 volt out, if we put 110 in, we would get, what would that be, 55 volt out. Now, with the lowering of the voltage on the output side, you also have a reduction with the amount of amperage you can pull out of it as well. So my guess is that this machine is manipulating with a computer essentially the voltage on the primary side, which changes the output on the secondary side, like I said, and that's how it's actually controlling amperage. Now, the old school transformer machines manipulated amperage by using a transformer with two halves, like say these are the coils, you have your primary coil, your secondary, and they either manipulated the transfer of energy by the distance between the coils to attempt to control the amperage, or they inserted some form of a magnet or a magnetic permeable material between the two coils that would increase or reduce the ability of the coils to exchange magnetic flux, if that makes sense. So by manipulating how much of that transfers, you can actually manipulate the output on the secondary part of the transformer versus the primary. Now, obviously, trying to manipulate that is going to be very inefficient, and you're going to have a lot of loss in electrical energy because that magnetic field is going to dissipate, and that's lost energy. So that's also why modern IGBT and computer-controlled welders are more efficient, because they're manipulating the primary side voltage or current essentially, which dictates output. So obviously that's more efficient than just losing it to the area around it. Hopefully that makes sense. So that hopefully gives you somewhat of a brief overview. This machine may function slightly different than this, but this is an overview of how it would be done. Older transformer machines, like I had said earlier in the video, like your Lincoln Tombstones and Ideal Arc 250s and all them transformer machines, they use far more inefficient transformers due to the frequency they operate at. and they don't have control with the IGBT modules to power the transformers, so they have so much less to work with. I mean, essentially whatever your wall outlet frequency and power is what they run on. And to convert to DC on those, they still have the transformer, and the DC output, they essentially just use a bridge rectifier, just like in this, to rectify it to DC. And also I'll depict here, there would be what's known as a choke module. So you would have a choke to take that dirty AC that comes out of the bridge rectifier, or capacitors. You could use capacitors as well, and to just try and smooth out the ripple in the DC output. And that's how the older school transformers work. It's just you remove the IGBT modules, just go straight from the wall to a transformer, and then that transformer is just bridge rectified with a choke or a capacitor to smooth the output out, and then you weld with it on DC. Now, if it's an older tombstone that does not have a DC output, then you get rid of this rectifier, and then you just tap straight off, essentially off your transformer directly out, because that is your output. You don't need a rectifier because that's to convert AC to DC. So pretty complex stuff, I know, and I probably went over this a little bit too fast for you, but I just thought I would mention that because I'm kind of disappointed that we couldn't really talk much about it. So like I had said earlier, these capacitors are either being used to smooth the ripple in the DC for the output, or they could be smoothing the DC that the IGBT modules operate off of. It could be that, but either way, that's what they're used for. In the case of this, is they're just used to smooth out the ripples that are created in the waveform. Like I said, this is your transformer. Your primary windings are probably, that would be the clear wire wrapped here, since there's more of them, and then the blue is your secondary windings. This down here is a choke that's used to smooth out the ripple, probably of the AC converted to DC. That's what that's used for. Beyond that, there's a lot of different things in here, but we can't really see most of them. But hopefully that took away a little bit of the mystery on this. And like I said, I apologize that I can't do a better video on this, but maybe down the line I'll have to pick up an old tombstone and we'll actually take one of those welders apart and test it, and I'll show you how everything works. But yeah, thanks for sticking around. If you got any comments, questions, whatever, feel free to leave them. Thanks.